Good morning, friends. Today we shall discuss about cogging and crawling in an induction motor. First, I will try to discuss cogging phenomena in an induction motor. This is the three-phase induction motor. Three-phase induction motor consists of two parts. One is stator part, and then a rotor part. And stator and rotor separated by air gap with few millimeter. And then this is the stator teeth. These are all stator teeth. These are all stator teeth, and this is the stator windings. And similarly, we have rotor teeth. Here rotor teeth. These are all rotor teeth, and then rotor winding is there. Rotor winding is there. And then whenever whenever we are giving the three-phase supply, and then what happen become this become stator and rotor acquires opposite poles. Stator and rotor poles separated by an air gap whenever you are giving the supply, and then magneto or MMF will be produced. Due to that MMF, whenever it will touch the rotor conductor, an EMF will be induced in the rotor conductor. Whenever EMF will be induced in the rotor conductor, current will start flowing. Current is there under a magnetic field means what will be created? An EMF will be created. Due to that, current start flowing. Current is there under a magnetic field means a torque will produce. Motor start rotating. Okay, so now this will acquire, stator poles acquire north pole, and stator poles acquire south poles, teeth acquire south, and then now what happen? Attraction will be exist between stator teeth and rotor teeth. Sometimes magnetic locking will take place. Magnetic locking will takes place. Such a phenomena what we call as cogging phenomena in an induction. Cogging phenomena in an induction motor. So this is the north pole, and this is the stator teeth acquire north pole, and rotor teeth acquire south pole. And then sometimes it will happen, not always. Even if you give full voltage to the motor will refuse to start due to this phenomena, cogging phenomena. Motor will try to refuse to start. Such a phenomena what we called as cogging phenomena. This will happen due to the magnetic locking between stator and rotor teeth. So this is the force attraction between stator and rotor, and then this is the torque developed. Whenever FC greater than this TD, what happen? Attraction will takes place. Attraction will takes place. This is the phenomena what we call as cogging phenomena. So sometimes it will happen even if you give three-phase supply and then full voltage is applied to the induction motor. Induction motor refuses to start due to this magnetic locking phenomena is what we call as cogging phenomena. Okay, so this cogging phenomena is predominant in case of squirrel cage induction motor because starting torque is very less in case of squirrel cage induction motor when compared to the slip ring induction motor. So therefore, cogging phenomena is very predominant in case of squirrel cage induction motor because of starting torque produced in case of squirrel cage motor is very less. Okay, so what is the remedies to overcome this phenomena? So to overcome this phenomena, a number of stator teeth should not be equal to rotor teeth. That one remedies. Number of stator teeth should not be equal to number of rotor teeth. Okay. Number two, you have to skew the rotor slots. You should not put in parallel. You have to make it in a skewed order. If you make it in not like this, you have to make it skewed order. Skewed, if you make it, this magnetic locking can be overcome. So this is the problem, and this is the remedies. So such a phenomena what we call as cogging phenomena. Cogging phenomena, this is an important concept in case of three-phase induction motor. Whenever you are giving three-phase supply and then motor is unable to pick up its speed means immediately you have to take the decision such that magnetic locking is taking place, and then you have to take the action. So such a phenomena what we call as Cogging phenomena. And another important phenomena occurring inside the induction motor is what we call as crawling phenomena. The crawling is also one phenomena. This is the three-phase induction motor, and then we are giving the three-phase supply to the induction motor, and then no, whenever we are giving the three-phase supply to the three-phase induction motor, no, rotating even, but even if you give it no, full voltage, motor unable to pick up its speed, and it will run with a speed of ns by 7. With a speed of n, suppose ns is 7 mean ns is 1500 means now it will 1500 divided by 7, that speed motor will try to run. Such a phenomena what we call as crawling phenomena. Crawling phenomena. Even if you give the supply voltage, full supply voltage to the induction motor, so what happens physically, motor will unable to, it will rotate with a speed of ns by 7. If it is run with ns by 7, it is immediately you can take the decision the crawling is happening inside the induction motor. So now here this crawling, why it occurs in induction motor? Because of harmonics, because three phase supply we are giving, and then whenever you are giving three phase supply, rotating magnetic field, this is the rotor and this is the stator, it is separated by an air gap, and then rotating magnetic field will be created due to non-linear magnetization characteristics, no, that non-linear magnetization characteristics of the induction motor here, that will be the non-sinusoidal waveform will be there. That due to that non-sinusoidal waveform, it will contain harmonics. So that is non-harmonics will be there. That is the reason due to that this phenomena will occur. So now we shall analyze one by one. So I already told you that the three-phase supply due to the non-linearized magnetization characteristics here it contains non-sinusoidal waveform. Non-sinusoidal waveform. So non-sinusoidal waveform is how we are analyzing. We are analyzing to the Fourier analysis. Fourier analysis, we know that if it is symmetry is there, even harmonic symmetry is there, rotating machine symmetry is there, then even harmonics can be or absent. Okay, and then whenever your three-phase induction motor given to the three-phase supply is connected to the delta connected load. Now you know that 3n 3 into n, where n is the integer, are absent whenever it is connected to delta connection. Three-phase induction motor is connected to delta. On that situation, what happen means 3n harmonics, 3 into n harmonics are absent. That means n is equal to 1 means 3, n is equal to 2 means 6, 3 3 is 9, like that. 3 4 is 12, 1 2 n, where n is 1 1 2 3 4 5, like that. N is equal to 1 means 3, n is equal to 2 means 6, n is equal to 3 means 9, n is equal to 4 means 12. These are all the harmonics are absent due to this phenomena. Three-phase supply, whenever you are giving three-phase supply to the delta connected, these harmonics also eliminated. Due to symmetry of rotating electrical machines, your harmonics will be absent due to the delta connected three-phase supply. Whenever you are connected delta connected, and then these harmonics are absent. Okay, and then remaining harmonics, what is the harmonics existing means this is the order of harmonics existing here. That harmonics existing here is 6a plus or minus 1, where a is an integer. Whenever a is equal to 1, a is equal to 1, what happen? N is equal to 6a, I will consider plus 1, and develops a torque in positive direction. Now 6a plus or minus 1 is there. 6a plus means develops a torque in positive direction. 6a minus 1 means develops a torque in negative direction. that is positive torque, what we call as forward torque, negative, what we call as braking torque. If you substitute A is equal to 1, so what we get it, n is equal, A is equal to 1 means 6 into 1 plus 1, n is equal to 7. And when you substitute A is equal to 1, so then you get n is equal to fifth harmonic. Fifth. So this seventh harmonic, when you substitute A is equal to 1, this will, A is equal to 1, that seventh harmonic, that is the forward torque with respect to the fundamental, but this will be, fifth harmonic, it will go in the braking torque will be produces. Braking torque will be produces. Okay, and then here I will analyze through figure here. This is the 6A minus 1. When you substitute A is equal to 1, you get a fifth harmonic. Fifth harmonic will try to produce the flux in this direction, opposite direction to the fundamental. When you substitute A is equal to 1 here, seventh harmonic will produce the flux in the forward direction. It will aid the fundamental. It will aid the fundamental. When you substitute A is equal to 2, when you get A is equal to 2 means 6 to the 12, 12 minus 1 means 11th harmonic. And then when you substitute here to this formula 6A plus 1, you get 2, 6 into 2, 12 plus 1, 13th harmonic will be produced. 11th and 13th harmonics are very small and can be neglected. And you know the speed torque characteristic of a three-phase induction motor with fundamental. With fundamental means how we get it. This portion is, this is the slip. So this is the torque slip characteristic of a three-phase induction motor with fundamental. Now, whenever slip is 1, you get a starting torque. Here, this one. This is the inverse. Torque is inversely proportional to 1 over slip. You get this portion. And then afterward, when it reaches the maximum torque, the torque is directly proportional to slip. Slip start decreases. So, torque also decreases. And then here slip is 0 and torque also become 0. You get already studied this torque slip characteristic of a three-phase induction motor. Here this is the starting torque, this is the maximum torque. Here torque is 0 because that situation rotor speed reaches the if it is reaches synchronous speed, there is no relative motion. So therefore the slip is 0, torque also becomes 0. And then during starting rotor speed is 0. Rotor speed is 0. That I am considering here. Then speed is increasing. If it is reaches rotor speed is equal to synchronous speed, there is no relative speed. So due to that, what happened means slip is become 0, torque also become 0. This is already studied. Torque slip characteristic of a three-phase induction motor with fundamental. This is the load torque we are putting on the machine. So this is the load torque we are putting on the machine. Here, if you observe, load torque is lesser than the starting torque. Motor will accelerate, will drive the load. And then this is the load torque we are putting. Here up to this point, no problem because motor torque is higher than the load torque. Motor will accelerate. After that, what happened here? So motor torque decreases. Now, up to this, it will pick up the speed. It will rotate and it will drive the load. After that, it's not possible because motor torque become lesser than the load torque. After this, not possible. So therefore, up to this, it will up to no problem. Here, it will motor torque will be produces and drive the load with the speed n. So this is the speed torque characteristic of three-phase induction motor. We are already studied. Okay, so now we shall analyze the concept of crawling phenomena. And this is the crawling phenomena. Here, crawling phenomena. This is, here, due to seventh harmonic, I already told you it will, this is torque speed characteristic of a three-phase induction motor with harmonic effect. So this is the seventh harmonic. I already told you it will produce a forward torque, and then fifth harmonic will produce a backward torque. That will I am representing this side. Okay, and this side, this is the seventh harmonic effect. And then here, so this is slip 1, this side is a braking, S is greater than 1, it is a braking concept. And then here, whenever rotor speed reaches synchronous speed, there is no relative motion, slip is 0. Slip is 0 means torque also 0. Now whenever n is greater than ns, it become enter into the generating region. So therefore slip is negative, and then torque also become negative. So this is I am not analyzing that, they are already stated braking region and regenerative region. So what we required is that the motoring region we required for practical concept, because motor is driving a load. So now here, this is the seventh harmonic effect. It is produced not torque with forward, and then this fifth harmonic produces backward torque. And here this is the fundamental. This is the torque speed characteristic with fundamental. I already explained here. This is the load torque characteristic. Now forward fundamental and seventh harmonic combined together, we get a speed torque characteristic. This is the speed torque characteristic of combined result of fundamental and seventh harmonic, because seventh harmonic and fundamental are in the same direction. uh, so now if you observe here, this is the uh, starting torque. Okay, and motor torque, this is the motor torque, and load curve here is there less than this, it will start. And then if you analyze up to this here, what happened here, TL is equal to TM, motor still it will drive it. But after this point, what happened physically, motor torque will be decreases. Motor torque will be decreases, so it cannot able to drive the load. Because if you analyze this portion, which one is dominating mean, motor torque, load torque is up to this, no problem. After that, what happened, motor torque will be lesser than the load torque, motor unable to start. And then it will try to run with the speed of ns by 7, ns by 7. So such a phenomena, or what we call as crawling phenomena in an induction motor. This will happen due to the harmonics, existing harmonic, due to the harmonic effect, this phenomena will be occur. So how to overcome this phenomena, that harmonic, if we eliminate it, then this problem can be eliminated. I think you already studied in the alternator now that winding is full pitched winding if it is 180 degree apart, and then you can make it as short pitched by an angle alpha. If you make it as a short pitched by an angle alpha, then you get a derivation. Short pitched angle is kc is equal to cos n alpha by 2. If you adjust alpha such that the seventh harmonic can be eliminated, seventh by adjusting alpha, seventh harmonic can be eliminated. So by making the winding such that by short pitching by an angle, you can eliminate the seventh harmonic. If you eliminate the seventh harmonic, automatically this crawling phenomena can be overcome. Crawling phenomena can be overcome. Okay, so therefore, even if you give full voltage to the three-phase induction motor, motor will run with a speed of ns by 7. It will run such a concept, what we call as crawling phenomena. Crawling phenomena. This will happen due to the harmonics. Thank you.